Hello, my name is Josfius Marvellous Kumendong. My number is 241011060085. I am a Class E Information Systems student, and at this time, I will explain about transistors and three logic gates, not, and/or, comma. So now we will go into the first discussion, transistor. A transistor is an electronic component that functions as a switch or signal amplifier. It works by controlling a larger electric current using a smaller electric current. The basic principle, comma, a transistor has three main parts: the base, the collector, and the emitter. A small current at the base can control a much larger current between the collector and emitter. This is similar to a water tap, where a large flow of water, collector current, can be controlled by opening or closing a small tap, base current. There are two main types of transistors, NPN and PNP. The difference lies in the type of charge carrier used. How it works, example of an NPN transistor. Asterisk when there is no current at the base. The transistor is off. No current flows between the collector and emitter. When a small current is applied to the base, the transistor becomes active on, allowing a larger current to flow from the collector to the emitter. Simple analogy, comma, think of a transistor as a water tap. A small current on the base is like our hand opening or closing a faucet, while a larger current between the collector and emitter is the flow of water coming out. Applications of transistors. Transistors are used in various electronic devices, such as computers, as switches to process digital data, smartphones, in various components, such as signal amplifiers, voltage regulators, etc., televisions, in image and sound signal amplifier circuits, radios, as oscillators and signal amplifiers, other electronic devices, such as remote controls, calculators, etc. The bottom line, transistors are very important components in modern electronics. By understanding how they work, you will find it easier to understand how various electronic devices work. We will continue with the next discussion. Three logic gates, not, and/or, dot.
And produce output according to a set of logical rules. One of the simplest logic gates is the NOT gate, represented graphically here. The NOT gate takes a single input, either a 0 or a 1, and inverts it, so that the output is the opposite of whatever the input is. If the input is a 1, then the NOT gate outputs a 0. If the input is a 0, then the NOT gate outputs a 1. To represent the logical rule this gate obeys, we can draw a truth table, which is just a way of writing down the rules for some logical formula. This table says that if the input is 0, then the output is 1, and if the input is 1, the output is 0. Often, though, our computers need to be able to perform calculations not just on a single bit of information, but on multiple bits of information. The AND gate, shown here for example, is a logic gate that takes two inputs instead of one. Let's call these two inputs A and B. As the name might suggest, the AND gate will output a 1 when both A and B are 1s, but in all other cases, AND will output a 0. We can construct a truth table here too. This truth table is a bit bigger, since with two inputs there are more possibilities to consider. If A and B are 0, the output is 0. If A is 0 and B is 1, the output is 0. If A is 1 and B is 0, the output is still 0, and only when both A and B are 1s is the output a 1. The OR gate, meanwhile, is also a logic gate that takes two inputs. This gate outputs a 1 when A is a 1, or when B is a 1. So if both inputs are 0, the OR gate outputs a 0. But if either of the inputs is a 1, or both inputs are a 1, then the output of the OR gate is also going to be a 1. These logic gates on their own follow fairly simple rules, but they can combine with each other to form more complex calculations. Imagine what would happen if, for example, we took two inputs, passed them into an AND gate, and then passed that output into a NOT gate. What would happen? If both inputs are 0, the AND gate will output a 0, and the NOT will turn that 0 into a 1. If only one of the inputs is a 0, nothing changes. But if both inputs are 1, the AND gate will output a 1, and the NOT will turn that 1 into a 0. In other words, this circuit appears to do the opposite of whatever the AND gate on its own would do. It turns out that inverting the result of an AND...
I think that's all for discussion. Hey, erase my video while I'm working with Blender.